Hi, in this example, I'm going to show how to use the OCR function from MATLAB and also some computer vision techniques to automatically detect text in natural images. This has applications on automated driving, but also in normal vehicles. For example, let's say that you have a distracted driver that parks in a handicapped parking. So with a function, with an algorithm like the one that I'm going to present in this video, the car can detect that you're in a handicapped space and trigger an alarm to move away to avoid getting towed. And basically the hard part of this is finding the subspace of the image in which the text is found. So that's what we're going to do. We're going to detect the letters and we are going to expand the bounding boxes around them to basically find the something like this, and basically find the bounding box that capture all the text, and this subpart of the image is fed into the OCR function to convert that into text. Of course, you can fit the whole image, but that might not be as accurate and not be as efficient. So doing this pre-processing computer vision detection can help finding this text, and then that text can be fed into some natural language processing algorithm or some database to do the rest of the system. Okay, so let's open the live script, and this takes us to here. So let's debug through it. I'm putting a breakpoint and hitting F5 so I can debug through it. And this is the image of the parking lot sign. We're going to convert it to gray so that we can use the MSER features. And the MSER features work well for finding text regions because they are consistent in color and have high contrast and are stable. So it fits perfectly. And in the references of this video, I have a link to this. MSER means maximally stable extremal regions. It's basically like working with blobs, and we're gonna see it in a moment. And unlike a brisk, fast, or orb in which they just return a location of the feature, this MSER returns blobs, something like blobs. And for example, in this case, we have a 1,119 blobs, and for each one of them, we have a location. I assume that is something like the centroid. We have axis, orientation, and count. This usually we find in other features as well. But let's take a look at the pixel list. Let's take the first one. Let's see the size. So we have 2,384 points for that first one. And let's take a look at the last one. So the last one have 565. So basically it's a set of coordinates that define the blob, and you can see it in here. And notice that is the regions and the features, but also we have a second object, and this is the connected components. And we're gonna see in a moment what that is used for. Notice that we have a connectivity of 8, and I'm gonna go back to this later, but the connectivity of 8 basically means that you're using the 8 neighbors rather than 4. The 4 neighbor is the vertical and horizontal, but the 8 one includes the diagonal as well. Okay, so let's just show the regions, and we're gonna display it with plot on top of the image itself, which is the sign image. Okay, so you're gonna notice that there's gonna be a bunch more than the text. So the text were detected correctly, but we also detected the handicap sign and also some lines in the wall. So we want to filter those out. Notice that the letters have the ratio between the width and the height is pretty square. And these lines, the width is much more larger than the height, so that aspect ratio can be used to filter out all these lines. So that's what we're gonna do. We're gonna pass the connected component. If we go to the help of RegionProps, we are using the second one option, which takes the connected components, and it says, okay, that's the object that is returned by BW connected component. In this case, we're not getting it from BW connected component, we're getting it from the type MSER features. And we can see here the structure that has a connectivity, an image size, number of objects, and the list of pixels, which is the basically linear indexes for the pixels for that component. Okay, so that's exactly the shape of this object that we're gonna pass to RegionProps that expects it. And notice that RegionProps expect a binary image, so it doesn't take the original image, it just takes the coordinates. And yes, they are linear indexes, but with the shape of the image you can infer the how that particular blob looks. Yeah, okay, so yeah, then that's because we only RegionProps is only interested in geometrical properties. Okay, so we're gonna determine what we're gonna get out of RegionProps by passing these parameters like bounding. We're gonna get the bounding box, eccentricity, solidity, extent, Euler, image. We're gonna get all that. So we have 1119 objects, so we get statistics for the same amount of objects, and you can see the bounding box in here, eccentricity, and the image. So for example, let's say that we want to see the number 100, the image number 100. Oops, okay, I was accessing it incorrectly, so it is like this. We're getting, let's say, the object number 100 and just getting the image of it. Okay, so that gives us a letter P. Okay, so yeah, that's a geometrical face, it's a binary image. And let's say that we want to see the 100, so we have a bounding box that describes that particular letter and some properties. So from the bounding box we can determine the aspect ratio. So we take the width, which is the third. Notice that this is in x minimum, y minimum, and the width and the height. So we divide this by this in all of them, in the 1000 plus objects, and so we have the same amount of objects in aspect ratio. And if you go beyond 3, means that the width is much larger than the height, and that's precisely what we want to do. And let's see what we got in here. So the values that are 1 are the objects that we're going to filter, and notice most of them are 0, so we're not filtering much. The first ones is the ones that we're going to filter, which should correspond to these guys. Okay, so we're going to do the same. If in addition to have a bad aspect ratio, you have a eccentricity higher than 0.995, we're going to filter you out. We're putting an OR into the filter index. If solidity is below 0.3, extent is below 0.2, and extent above 0.9, or Euler number below -4. So we're gonna filter all that. Okay, so let's see how the filter looks. Yeah, very few objects. So basically, wherever that value is 1, we're gonna put it to empty. So that means that we're gonna take it out. We have 1119 objects, so we're gonna get much less now. Not for that many. We only now we have 1041 objects. Okay, so let's see how it looks, and it should look much better now. Okay, so yeah, so we see that the lines, those bad lines, are gone, which is good. And I think most of them were gone because of this aspect ratio rather than the other ones. Okay. So now let's filter some more, and there's a technique that the example described called a stroke width variation. And at this point we have 1041 objects, and this ends up filtering only 10 and doesn't make much difference, but it might make difference in maybe other scenarios. Maybe the more you filter, the more efficient it becomes. So okay, I'm not gonna give much details about it. he's basically gonna use the distance, BW distance, with some MATLAB function to get the distance between 2 points, and then it's gonna use some morphology. This technique, stroke width variation, I'm gonna put this definition in the reference. Is basically in character recognition, the distance between two edges of a stroke measured perpendicular to the stroke center line. So understand that basically it's trying to get the center line by using this morphology thing operation to get a skeleton-like image. And let's take a look at the skeleton image. The distance image looks very similar to original image. It's like a vertical line in the center of the character, and then that the opposite is applied, is used as an index for the stroke image, which is the distance image. And then after that, it's gonna take the standard deviation of that divided by the mean, and with that, if it goes above a threshold, it's gonna filter it out. So you can see the character here, and this, I think this might be called the stroke in, yeah, the stroke width image in the region image. So with that, you get the skeleton image. Use it as a, this is the skeleton image, and you're gonna use it as an index here to get the stroke width values, and then you get the ratio between the standard deviation and the mean. And if you are above a threshold, then you're gonna get filtered out because you're not a character according to this metric. Okay, so what it's gonna do is apply all that thing, getting the BW distance of the image, the thin skeleton image using the distance, and then get the metric. And it's gonna get an array for each of the 1000 plus objects to filter them out. So let's take a look. Let's just run it and see how much does that buy to us. And we're gonna see not much. Most of them are 0. So let's take a sum of them to see how many we're gonna, actually 10 of them, as I mentioned before. So for each of those 10, we're gonna send to empty. So now instead of 1041, we're gonna get 1031 objects. Not much difference, and we're gonna see it in here that the difference is not that much. Okay, yeah, it's basically almost the same. Okay, so now we're gonna merge the regions. So we're gonna take the bounding boxes of each of these regions, and we're gonna expand them to basically make them touch each other both horizontally and vertically. And basically using the connected components function, we're gonna find the bounding box that surrounds all the text. And also we're gonna find another region here and another region here. We're gonna find 3 of them. Okay, so let's take first the bounding boxes. Okay, so we have 1031 bounding boxes, and the bounding boxes are in the format of x minimum, y minimum, width, and height. So we're gonna convert them for convenience into x min, y min, x max, and y max. We're gonna use all of this later. Okay, so for getting the maximum, we just add the width to the minimum and the height to the y minimum minus 1, and then we're gonna expand it by 2%. It's gonna be 2% less in the upper left side and 2% more in the lower right side. And then because of that expansion, we can go out of bounds, so we get the maximum with 1. We'll clip it with 1 and clip it with the maximum size. And now that we have expanded, we're gonna again change it into the format of x, y minimum and the height, width, and height by subtracting the maximum and minimum. Okay, so now we're gonna insert those new expanded boxes into the original image and see how they look. And you're gonna see that with that they collide better, and now we can basically get the region. And for that, we use a function called bounding box overlap ratio, which basically compare all bounding boxes with all bounding boxes and see which one are colliding. And we got the ratio, which is a table, and as you can see, the diagonal is the bounding boxes that are the same, and for that, of course, you're gonna get the overlap ratio of 1. And as you go far away, they collide less and they do not collide at all. So with that, of course, we don't want to compare the boxes are one box with itself. So we are going to put the diagonal into 0. And now that table, 131 by 131 can be converted into a graph of nodes and edges. And you can see it in here. And with that, we can use the connected component with the graph, and we're basically it's gonna find out which of those objects that are that touches basically which I mean which touching bounding boxes belong to the same group. So with this, it's gonna find, for example, this is connected to this one, this is connected to this one, but this is connected to this one. So basically, they form like a connected component. So this is gonna be one group, and this one is another group, and this is on its own island. Okay. So with here, what this is gonna give us is that for each bounding box, we're gonna have 131 components. So for each bounding box, you're gonna see a lot of ones in here. Okay. And the number 1 is the biggest one. So let's take how many unique values we have in here. So we have 1, 2, 3. So we have 3 groups. The one which is the more frequent is this one, the one with the text. Okay. So now let's use this funky function. I have the description of that function in the as a reference. So what this function accumarray is gonna do is that, for example, let's say that we have array of data and 1, 2, 3, 4, 5, 6, and we have an array of indices indicating to which group each element belongs. So by default, accumarray is gonna use sum, but yours can also provide a predicate function. So in this case, for example, this is the first group. So it's gonna sum all the elements in the first group. So the first group is gonna be 1 plus 6 is 7, and the fourth group. So we only have only four groups in here. So the fourth group is this. This belongs to the fourth group. The third one belongs to the fourth group, and this one. So 3 plus 5 is 8, and the fourth group is gonna be 8. So basically, what it's doing is gonna for each of the 3 groups that we have in here, the 3 groups again are this one, this one, this one, and this one. So for each of the 3 groups, it's gonna take for the minimum coordinates, which we have the minimum for the 1031 objects. It's gonna take the minimum value, and then the minimum y, and the maximum x and the maximum y, because we're passing these minimum maximum functions for each of the 3 groups of each of the indexes that we have in here. So what that's gonna give us is the bounding boxes for the groups. So it's gonna take the minimum from all of these boxes. It's gonna take the minimum, which is gonna be this here, x minimum, y minimum, and the y maximum, x maximum. So that gets us the bounding box. And same here. Okay, so we have 1031 objects, but we're gonna expect 3 outputs here because we have 3 groups. So you can see it in here. Only 3 values, and the same. And then finally, we're gonna take all of them and create the 3 bounding boxes by taking the difference. We get the width and the height. So we got our 3 bounding boxes. And now we're gonna get the histogram count, so basically the frequency of each one of them. And this is gonna try to filter, but it doesn't really do anything. We can see the frequency here. Of course, the first group is the one that has the text and has the maximum frequency. So what I will do in here is basically say, okay, if you have a frequency of less than 50, then I drop you out. But it didn't drop it out. But it doesn't make a difference. You're gonna see why in a moment. So the bounding boxes are put in top of the original image, and we're gonna see how they look. And effectively, we got our text separated. Okay, now we're gonna feed those three bounding boxes along with the original image to the OCR. And notice, and let's see what that gives us. Okay, so notice that the second and third group are empty because there's no text in there. Okay, so we could have filtered it out, and notice that we did a lot of filtering with eccentricity, with with the concept of stroke width and all of that. But still, even if you fail to filter things out, you're gonna get empty. So it's up to the person to how much filtering you want to do before passing it to the OCR. And then the bounding box that didn't matter, we did get the text. So of course, this might be fed to some natural language processing algorithm, to some preprocessing. For example, in here we get handicap. That's a typo. That had to be fixed automatically. Handicap parking special plate required unauthorized vehicles may be towed at owner's expense, and this you can feed to a database or some algorithm to determine if you're gonna tell the user that you should move out from that parking lot. Okay, that's all the example. Thank you very much for watching. Bye.